Okay, maybe I'll get started. Today's class, we're going to start talking about the pendulum, and we're actually carry on talking about the pendulum in both of next week's classes. Specifically, we're going to be talking about the numerical solutions of the ordinary differential equation for the pendulum. And we're going to begin with it in this class and then carry on with it next classes. In today's class, specifically, we're going to solve numerically the damped-driven pendulum ordinary differential equation, and we're going to focus on some of the basic features, characteristics of that system. And then in next week's classes, we'll return to the damp-driven pendulum in the nonlinear domain, and we'll explore kind of the world of chaos and nonlinear equations, nonlinear dynamics. So a lot of the stuff for today, whilst you might not have solved the damp-driven pendulum numerically, you probably met the pendulum and lightly the damp-driven pendulum in other classes. So just a few kind of general remarks on why we're interested in the pendulum. So I put, I mean, this is kind of a joke, but not. Is it because we're nostalgic? Is it because we like swings? It could be. The pendulum over the past few hundred years has been very important. It's how the density of the Earth was first explored through the pendulum. It's how the rotation of the Earth was seen in a sort of terrestrial experiment. It's how they detected distant earthquakes, and it's played a role in the sort of scientific development, the economic development of civilization through precision timing. So there is nostalgia about it. It has been important. You probably met, I'm sure, in high school that the pendulum exhibits periodic motion, regular motion, and that was first analyzed by Galileo. You might not have met probably haven't met in high school that the pendulum exhibits irregular motion, and in a sense that was first explored by Huygens, and so that'll be kind of the new stuff. The point is that our mathematical kind of analytical treatment of the pendulum is often a idealization of a pendulum. And what we're going to explore over the next week and a half is really stepping beyond that idealization, that analytical idealization, to the kind of nonlinear dynamics of the pendulum, which is a new science of the last decades. And the pendulum is kind of the classic example where the theoretical aspects, experimental aspects of non-linear dynamics are quite accessible. And so that's the reason we'll talk about the pendulum. Okay, so just some basic things about the pendulum so that we're all on the same page. I sketched out a pendulum here. This is a simple pendulum with a pivot at the top, a support, a string, a cable, and a pendulum bob here. And that pendulum bob is experiencing two forces, gravitational force and tension force. And the net force that results from the superposition of the two forces, the gravitational force and tension force, is what provides a restoring force. That if you displace the pendulum towards the right, there's going to be a restoring force back towards the equilibrium. If you displace it towards the left, then there be a restoring force back to the equilibrium on the right. We often, when we think about the pendulum, we think about this sort of idealized pendulum where, for example, the pivot has no friction, it's frictionless. The string, spool, that's idealized as rigid. It doesn't stretch as the pendulum swings backwards and forwards, and it's idealized as massless. It contributes no mass. And often we idealize the pendulum bob as like a point-like mass rather than a distribution of mass. So there's, in the simple pendulum, there's lots of idealizations that often we don't think about anymore, but there's lots of idealizations in the problem. Okay, so I wanted to turn to the second order ordinary differential equations describing the pendulum. And I'm going to kind of build them up in layers. So this slide is about the simple pendulum. Next slide is about the compound pendulum. Then we'll come to the damped pendulum. And finally, we come to the damped driven pendulum. So we'll sort of build up the layers of the second order ordinary differential equations. So the restoring force causes an acceleration of the pendulum bob. And through Newton's second law of motion, F equals ma, and knowing that restoring force, it's a component of gravity, mg sine theta, we can write down the second order differential equation here that describes the simple pendulum. So this is just Newton's second law, right? Rearranged a little bit. This is basically that the force, the restoring force, determines the acceleration of the pendulum through Newton's second law. So here's the acceleration, and here's the g sine theta of the restoring force. And actually, in this equation here, I've cancelled out the mass in the force of gravity and in Newton's second law. So this is the differential equation you get by just directly substituting the restoring force into Newton's second law of motion. If the angle that the pendulum swings through is small, maybe that's sort of a few degrees or maybe up to 10 degrees. If that angle is small, then you can approximate sine theta, which came from the restoring force, with theta, and then you get this differential equation down here, this simpler differential equation down here. And the distinction between these two is important, and we're going to return to it. The first equation is a non-linear second order differential equation for the pendulum motion. So the expression involving theta is non-linear, sine theta. The second equation is a linear second order differential equation. It's linear in this, this angle theta. And it's typically these ones that not the linear second order differential equation that we meet and look at the solutions to the differential equation. And so you know these solutions, right? That the solution is a sinusoidal function, cosine or sine function. It has a character, so it's a periodic oscillation, has a characteristic frequency omega, angular frequency omega, that depends on the acceleration of gravity and the length of the support, so square root of G over L. And then the other parameters in this solution, the amplitude of the oscillations, the phase of the oscillations, that make this a kind of a family of solutions. they're determined by the initial conditions of the pendulum. So the initial angle that the pendulum is released from, the initial velocity, angular velocity that the pendulum is given. And it's important that this simple solution of the simple pendulum has this property that the period or the frequency is actually independent of the amplitude of the oscillation. So that's a famous sort of consequence of this differential equation. Also, you notice in this solution that the solution is independent of the mass of the pendulum bob. I canceled out the mass of the pendulum bob. Actually, that's kind of interesting because when I'm canceling out the mass of the pendulum bob, I'm making the equivalent, the gravitational mass that enters into the gravitational force on the bob with the inertial mass that's present in Newton's second law of motion. So inherent in my solution is the equivalence principle that the gravitational mass and the inertial mass are the same. Okay, so simple pendulum. Compound pendulum. So compound pendulum is just the case of a simple pendulum that now has a distribution of mass. It can no longer be considered a point mass. But basically, the equation for the compound pendulum differential equation is the same as the equation for the simple pendulum. The way you analyze the motion of the compound pendulum, I'm going to go through this pretty quickly because it is just the parallel of the simple pendulum, is think about the torque, the gravitational torque on the compound pendulum, like you thought about the gravitational force on the simple pendulum. So there's a gravitational restoring torque on the compound pendulum, like there was a gravitational restoring force on the simple pendulum that tries to return the compound pendulum, like the simple pendulum, towards the equilibrium. And if you use Newton's law of rotational motion rather than Newton's law of translational motion, Newton's law of rotational motion relates the torque to the moment of inertia times the angular acceleration, just like F equals ma is relating the net force to the linear acceleration. If you use that, the combination of Newton's law of rotational motion with the fact that we've got a restoring gravitational torque here, you get this little equation downstairs here, this differential equation here. And the new ingredients are, well, now our compound pendulum is described by, it's a distribution of mass, so it has a center of mass, that's this L subscript Cm. It's a distribution of mass, so it has a moment of inertia, that's this I about the pivot point, the subscript PVT here. But this is just Newton's law of rotation, like the previous slide was Newton's law of translational motion. If, again, you make this approximation that the angle of the compound pendulum during the oscillations of the compound pendulum is small, a few degrees, maybe up to 10 degrees, then you can make the approximation that the sine theta in the upper differential equation is approximately theta. And then you get this linear version, it's linear in theta, linear version of the compound pendulum's motion. And so again, these equations are importantly different, because one is a nonlinear equation, ordinary differential equation. The second one is a linear ordinary differential equation. The analytical solutions for this compound pendulum have exactly the same form as the simple pendulum, because the ordinary differential equation has exactly the same form as that for the simple pendulum. The frequency is again determined by the parameters of the pendulum. So in this case, it's going to be the mass, going to be the center of mass, going to be the moment of inertia, and the acceleration of gravity. And then the amplitude and the phase of the oscillations. Again, there's a whole family of different amplitudes and phases that are determined by the initial conditions of when the angle that you release the compound pendulum from and the initial angular velocity that you gave the compound pendulum. Okay. So that was the compound pendulum and the simple pendulum. And in both cases, we looked at the first differential equation we wrote down was a nonlinear differential equation, involved the sine of the angle that the pendulum made with the vertical. And then we approximated that to the second ordinary differential equations that we wrote down. Those were linear differential equations, where the equations are linear in theta. That is, I wanted to stress that that's a big difference between those two differential equations. Some of the consequences. So a consequence has to do with the frequency of the period of the oscillations. So for the linear case, the frequency, the period, is independent of the amplitude of the oscillation. So that's kind of a feature that makes it useful for timekeeping. For the nonlinear case, the frequency of the period is dependent on the amplitude of the oscillation. So if you make the amplitude of the oscillations bigger in the nonlinear case, then the period gets longer and the frequency gets shorter. So in the nonlinear case, you don't have this the system isn't characterized by a single frequency. And another important difference is that in the linear case for the simple or compound pendulum, the oscillations are described by a single frequency, a single sine wave or cosine wave. There's just one base cosine or sine wave describing theta as a function of time. In the nonlinear case, that's not true. The motion is periodic, but it is a superposition of various sine or cosine waves, various harmonics of a kind of base sine wave. And so that's a second big difference, characteristic of the nonlinear solutions. Another important difference between the nonlinear and the linear equation is in the linear case, if you have, say you've got solution number one for the differential equation, you've got solution number two for the differential equation. The sum of those two solutions is also a solution of the linear differential equation. That's not true in the nonlinear case. If you've got solution number one of the nonlinear case, solution number two of the nonlinear case, you add them together, you don't get a new solution of the nonlinear case. So that's a big sort of more mathematical difference. It's this characteristic of the nonlinear ordinary differential equation that I try to think of it as kind of a straw that breaks the camel's back, right? That nonlinearity is what causes transition to chaos. And so the nonlinear differential equation exhibits chaos. The linear differential equation doesn't exhibit chaos. And as you turn up the nonlinearity, like as you add, straws to the camel's back, there's some point that the system collapses into chaos. Okay, so now I want to add some real life features of real life pendulum to as simple pendulum or a compound pendulum. That's the next two slides. One is damping and one is a driving force. So a real life pendulum doesn't swing backwards and forwards forever and ever. A real life pendulum, there is resistive forces that damp the energy, dissipate the energy of the pendulum. So that's what's introduced on this slide. So if you remember back to the description of free fall, we added to that description of free fall a resistive force, a drag force. And there we talked about the a linear drag force, and we talked about a quadratic drag force that were proportional to V and V squared. You can do the same thing for the simple compound pendulum. You can think of a resistive or a drag force that is in proportion to the velocity or the square of the velocity. Here we're gonna treat the resistive force as proportional to the velocity, proportional to the angular velocity. So I'm going to add an extra term to my nonlinear upstairs and my linear downstairs differential equations. So the extra term I've added is this piece on the far right in both cases. So this is a piece that's proportional to the theta dt. That's the angular velocity. It's the rate of change of the angular coordinate. So here's a term that's proportional to the angular velocity. So it's going to be large drag when the pendulum's swinging fast, less drag when the pendulum's swinging slowly. And we're adding that. And just like in the case of the falling body, we had to introduce some constant that depended on whether we're falling through air or water or whatever. We have to add some constant here that characterizes the particular pendulum and what it's moving through. So that's that constant beta. And the 2 is just the convenience. So that's how we introduce damping. There are 3 important categories of damping that are kind of interesting. And we call them underdamping, critical damping, and overdamping. And part of the reason for the 2 is that underdamping is when the damping constant beta is smaller than the natural frequency of the oscillator, of the pendulum. Overdamping is when the constant beta is bigger than that natural frequency of the pendulum. And then critical damping, that's when the beta and the natural frequency are equal to one another. So there's these 3 categories. And what's kind of interesting is that only underdamping exhibits oscillatory motion. So if you release a pendulum and the restoring force leads to an underdamped situation, that pendulum will oscillate to and fro and its amplitude will slowly die away. In the case of critical damping and overdamping, that's where the damping resistive forces are larger. Then you release the pendulum and it doesn't oscillate to and fro. It just works its way back to the equilibrium. Critical damping is where it works its way back to the equilibrium on the shortest time scale. And actually, if you have even more damping force, it takes longer to work its way back to the equilibrium. So critical damping is kind of important in mechanical systems, like it's suspension on your car, right? You go over a bump, you don't want it to be vibrating forever. You want it to return to the equilibrium as soon as possible. We try and critically damp it. So it's very important in mechanical systems. Downstairs here, right at the bottom, I wrote down the solution for the linear equation in the case of underdamping, where you get oscillatory motion. So it's this solution here. So you see the familiar sinusoidal oscillations with some frequency, but you see the amplitude of the oscillations is going to decrease with time exponentially in a way that depends on the damping constant. So if you set the damping constant to 0, then it will keep oscillating forever. But as you just turn up the damping constant, it's going to, the oscillations are going to fade away faster and faster. This frequency here is smaller than the frequency of the corresponding undamped pendulum. And it's smaller by an amount that's determined by the damping constant. It's given by this little equation here. So that's a case that also can be solved analytically. Final slide on the sort of theoretical framework for the pendulum, and that's to do with adding a driving force to the pendulum. So if you push a child on a swing, then your push is a driving force on a pendulum. In mechanical clocks, nobody has a mechanical clock now, but mechanical clocks suffer from damping. You have to have a driving force on, say, the pendulum in a mechanical clock. So driving forces on pendula, a common situation. So in this slide, we started with a simple compound pendulum, just oscillating to and fro forever. We've added the damping resistive force to the pendulum so that the oscillations will die off fast or slow. And now we're going to drive that pendulum with some external, we're going to drive it with some external oscillating force. So the force I'm going to imagine has this particular form. So it has some characteristic strength and some characteristic time dependence. It oscillates, it's sinusoidally with some frequency I'm going to call the frequency of the restore of the driving force. So that's the omega f. This is not the natural frequency of the pendulum necessarily. This is not the that damped frequency of the pendulum. This is some frequency for the driving force that if you're setting up the driving force, you set up this frequency. Okay. So upstairs here is the nonlinear version of the damp-driven pendulum differential equation. Downstairs here is the linear version of the damp-driven pendulum differential equation. The only difference from the previous slide is I've added this extra piece that I put on the right-hand side of the equal sign. So it's here and it's here. This is the piece that is the driving force. And so you see the magnitude of the driving force, you see the sinusoidal nature of our driving force, you see it's the frequency of the driving force. So an interesting thing happens when you apply a driving force to a pendulum. Suppose we've got a pendulum, it's swinging backwards and forwards, and we switch on the driving force. So, suppose you've got a child going swinging backwards and forwards, and then you start pushing. There is a transient period in which things change. And the change is that before we apply the driving force, the pendulum is swinging backwards and forwards with this natural frequency. That's going to change to the pendulum swinging backwards and forwards with the driving frequency. So typically what you see when you apply a driving force is some transitory, sort of complicated period with that lasts some finite time in which the natural frequency evolves to the driving frequency. And then after that, you just see a oscillation with a certain amplitude, with a certain phase at the driving frequency. And I've written down here, so these two equations here, this is the amplitude once you get to that steady state. You got past the transients. This is the phase once you get to that steady state, past the transients. This is the amplitude of the driven oscillations. So see, it depends on the driving force and the frequency of the driving force. and the natural frequency of the pendulum. And this is the phase. This is the phase with respect to the phase of the driving force. And so the phase is not in general identical, is given by this expression here, that depends on the natural frequency, the driving frequency, and the damping constant. So a classic example of a situation with, say, a simple compound pendulum that's damped and driven is the case of mechanical clocks, right? Mechanical clocks, inevitably, there's damping resistive forces, so they're at play. In mechanical clocks, to keep the mechanical clock going, you need a driving force to keep it oscillating. And so Huygens is famous for inventing the sort of first kind of mechanical clock that I think was accurate to, I think up to then they were using pendulums and things like that, but they're probably accurate to like an hour per day or something like that. But he developed one in which the driving force kind of supplies the energy, that the damping force is dissipating, and produce the precision timekeeping piece.